I think there are some misconceptions we can definitely clear up. I think some good things to help you with. Walking around, noticing there's definitely been kind of a reverting back to some middle school habits, and I want to try to help you with that. And then also what the Pythagorean theorem, how it applies here to this one. So let's review some parts of the triangle. Does anybody know what the longest side of a right triangle is always called? Hypotenuse. And so the hypotenuse is always directly across from the right angle. So this side over here is the hypotenuse, like so. And so, like I said, that's always going to be the longest side. It's always going to be the side across from the right angle. And the other two sides are shorter than the hypotenuse. The other two sides, does anybody know what the other two sides are called?
Doesn't one of those start with an I?
Base and height, I guess you could, yeah. They actually start with the letter L.
Oh, yeah. Lengthen.
They're both called legs.
Legs.
So there's two legs and the hypotenuse. So where I think we run into issues is here. You guys all, I think you all remember from middle school, the Pythagorean theorem is what applies here. It's a squared plus b squared is equal to c squared. And I think misconception number one is that we've kind of been conditioned that the c over here is always the unknown. And that's not always the case, actually. It could be something else. And so as you fill out the Pythagorean theorem, I noticed that folks that were like well-meaning and had a good idea of what to do, but made a mistake, did something like this. They said 12 squared plus 13 squared equals c squared. And that tells me you're not quite making the connection with which parts of the Pythagorean theorem go with which parts of the triangle, right? So, bless you. This would be not good, because what you've done is you've put the 13 in place of one of the legs, and the 13 is the hypotenuse, right? So I think a better way to say the Pythagorean theorem is not a squared plus b squared equals c squared. I think the better way is to say leg squared plus leg squared equals hypotenuse squared. Something like that. I think that's maybe a better way to think about it. Maybe you can get all the different pieces in where they're supposed to go and go from there. So with that in mind, I'm going to say that my first leg is x, so that's going to be x squared. And my second leg is 12, so it would be plus 12 squared. And then my hypotenuse is 13, so that would equal 13 squared. So that would be a good starting spot. The x could be where it is, or it could be where the 12 is. The x and the 12 could swap, but the 13 needs to be where the 13 is, because that's the hypotenuse. So you do a little arithmetic here. 12 squared is 144. 13 squared is 169. Notice how I'm keeping a really nice equation through here. My equal sign is not disappearing. I'm keeping it balanced, and I'm trying to show some good habits and good steps with algebra. If I'm trying to get the x by itself, I'd subtract 144 from both sides. Again, I'm not going to lose my equal sign. I'm going to maintain that right there. And finally, I get to this x squared equals 25. How do I get rid of the squared?
Do a square root.
And this was kind of the new thing from last time. So we do a square root of both sides. And so because this is the side length of a triangle, we go with x is equal to positive 5 for that missing side, that missing leg. Okay, so saw a lot of 5s. Definitely saw maybe some shaky work, some kind of middle school habits came through where we weren't showing correct steps on an equation. You want to be showing that for sure. But there you go. There's your Pythagorean theorem. We doing okay? This is really just like what we started with that wall last time. Okay, so if there's no questions, we're going to move on. We good? Okay, so we're going to move on to what you guys watched in the video, and I just kind of want to see how you're doing with this. So here's all the video material right here, those two questions. And I thought we'd start off with number 3. And we're going to just practice a little bit. And I want to see how you all do with this. And if you didn't watch the video, this could be a massive, massive struggle. Or hopefully not. I don't know. Maybe you did some of this before. Maybe you did, maybe you didn't. But I thought we'd start off with this, see how this goes. We're going to simplify this radical to its lowest, most simple terms. So give it a shot. No calculators really allowed on this one. As long as you can do things like divide by 2 or divide by 5, you should be okay. The calculator is not really going to help you here beyond that. So give it a shot, be around to help, and we'll explain it in the end. Ladies, gentlemen, let's get started. So the way that you handle this is you want to break it down into prime factors. So the way I showed you on the video, there are lots of ways to do this. I would say that there's 2 main ways to do this. I found that this is a great way for folks that are kind of starting off with this to be successful. So if you do this off to the side, that's cool. If you do a factor tree, a factor ladder, if you can do this in your head, that's fine. But what we want to do is we want to arrive at this idea right here that 20 is really 2 times 2 times 5. If you break that 20 down into its prime factors, again, use a factor tree, a factor ladder, whatever, to get to that point. But that's your prime factors of 20. Then the next to the 5th is just x times itself, 5 times. There's a 4th time. There is a 5th time right there. So there you go. Once you have broken this down into its prime factors, because it's a square root, you're going to be hunting down groups of 2. Groups of 2. So for example, there's only a single 5, so we're not going to be able to find a group of 2 5s, right? We're not going to find a pair of 5s. So that's not going to work. But I'm sure you noticed that there are 2 2s, aren't there? And not only are there 2 2s, there are 2 x's. There's a group of 2 there. And then isn't there a whole other group of 2?
Yep.
So this over here, that would be another group of 2 x's. And maybe you can see now at this point that there is nothing to pair with the 5, and there's nothing to pair with that last x. Make sense? Okay, so here's how we handle this. If you have a pair of 2's, a pair of 2's inside the radical, outside the radical will just be a single 2. The reasoning for that is really, isn't 2 times 2 4? And the square root of 4 is 2. Okay, so to get that out of the radical, it's just going to be a single 2 out there. And then this pair of x's right here would come out of the radical as just a single x. So that would be times x. And then this last pair of x's, again, would come out as a single x. The radical is still there. And the 5 didn't have anybody to pair with, so the 5 couldn't leave. And the x didn't have anybody to pair with, so the x is still there as well. So maybe a final last step here would be to recognize that x times x is x squared. You'd end up with 2x squared times the square root of 5x. There are all kinds of cutesy analogies I can use here to help you if that's not making sense. Do you have any questions? Anything? Did that all make sense? Okay, cool. So 2x squared root 5x. I would liken this to like reducing a fraction. We've just reduced this radical to its lowest, most simple form. And we'll talk about why we would do that here in a little bit. But for now, we're going to just be working on reducing it to its most simple form. Okay? So numbers 4 and 5 next. Why don't you give those a try, numbers 4 and 5. And we'll kind of regroup here in a second and see how it all went for you. Let's review this. We'll do some practicing here in a little bit. Here we go. 27 is 3 times 3 times 3. So when you look inside the radical, there's really only one pair for us to consider, and that would be a pair of 3's. So that pair of 3's can come out as a single 3, so it'd be 4 times 3 times the square root, and then the leftovers inside would be a 3 and an m. Those are left over because they did not have anything to pair up with. So 4 times 3 being 12, I'd end up with 12 times the square root of 3m. And walking around, peeking over shoulders, talking to you, I saw that answer a lot. So it feels like one way or the other, whether you learned a lot from the video or you learned this from last year or you combination of the two, whatever it is, you're doing okay. Am I reading this correctly? That's very good, of course. Okay, encouraging for sure. Okay, let's take a look at number 5. Number 5 is a little bit more complicated. It's got that fraction out front. What is the operation between the 1/6 and the radical? Is it 1/6 plus the radical?
No.
1/6 times?
Yeah.
Yeah?
Yeah,
It is
it's
1/6 times. That's pretty important. Because if it was plus, this would be a pretty different question. So the 72 is 2 times 2 times 2 times 3 times 3. And then x to the 8 is a bunch of them there. X times x, there's 4 of them. There's 6 of them, 7, and 8. All right, so you're looking for pairs of like elements. So I'd say that there's 2 2s, there's 2 3s, there's a pair of x's, more pairs of x's. We get something like that. Okay, so the 1/6 is still there. I'm not going to let that go anywhere. But if I've got 2 2s in the radical, when they come out, how many 2s are there?
1.
There's 1 2. All right, so times 2. And then there's 2 3s. Those get to come out as a single 3. So times 3. And then aren't there 4 pairs of x's?
Yes.
1, 2, 3, 4 pairs of x's. So that would be times x to the 4th. Remember, because each of those pairs comes out as a single x. Left over inside that radical is
2.
a 2. That's it, right? Everything else had something to pair up with, and it got to come out of the radical, and the 2 is the only one who didn't. All right, so then 2 times 3 is 6, and 1/6 times 6 is 1. So we end up with x to the 4th times the square root of 2 as our most simple version of this radical. Okay, how are we doing? Any questions at all? Okay, to the board, let's practice.
Can I come to the board now?
She's dating White Johnson.
Simplify it. Whoa.
This final concept we're going to be looking at, this final skill, is called the quotient rule for square roots. And this is essentially answers the question, what if you had the square root of a fraction? Really all it is. So here it is. Here is the rule. So if you have the square root of a fraction, like the square root of a over b, then you can break it down a little bit. You can break it down if you want. Sometimes we'll do a preliminary step or two, but you can break it down into the square root of a over the square root of b. So square root of the top, square root of the bottom. In a lot of cases, this will make it pretty simplistic. Like I said, sometimes there will be a step before this. I think we'll do one like that. But this is your basic idea of the square root of a fraction. So if you would, take a look at number 6. Number 6 is the square root of, it looks pretty scary, 108/25. Well, here's what we're going to do. We're going to start off by saying, if we're doing the square root of a fraction, we can do the fraction of 2 different square roots. So we could simplify this to be the square root of 108 over the square root of 25. Square root of 108 divided by the square root of 25. So right off the bat, square root of 25, isn't that something, doesn't that register with you? What's the square root of 25? 5. Yeah, this is one of those perfect squares. So we could then say, all right, well, this is really square root of 108 divided by 5. Now, the root 108, we're going to have to do a little bit of work. We need to do some prime factors of 108. Maybe I'll do that off to the side. What number goes into 108? 2. 2 does. It's obviously even. So 2 times what is 108? 54. Is 54 still even? So let's keep rolling with the 2's. 54 is 2 times what?
20.
27. And 27 is really 9 times 3. And 9, of course, is 3 times 3. So if you can break that down in your head, no problem. If you want to do a factor tree, of course, no problem either. So square root of 108 would really be 2 times 2 times 3 times 3 times 3. So then we use the same kind of strategy we have been taking. We're going to be looking for pairs. So I'm looking for 2 2s, looking for 2 3s. There is an extra 3 right there. And hopefully this makes sense as far as how we finish this. The pair of 2s comes out as a single 2. The pair of 3s comes out as a single 3. So it would be 2 times 3 times the square root of 3 over 5. So perhaps my final simplification here would be 6 root 3 over 5. Grace.
Sorry. So when we're like writing it out on like a test or something for like full credit, do we have to write it this way, or like can we write like the prime factor or whatever to the side and then just add it back in?
Totally.
Okay.
Yep. Totally can do that. Absolutely. Questions from anybody? I hope you're seeing the similarities with what you guys did at the start with what we're doing here. Okay. Why don't you take a look at number 7? I want to help you get started with 7, and then I'll let you finish it out. Okay, number 7 says simplify completely. Here's what I want you to notice. I think this is a really excellent review of stuff we've done in the past. I think it's definitely worth our while. Take a look inside the radical first. You obviously see a fraction. Listen, don't just race off, please. Those of you that are writing right now, I don't think you should be. Maybe you should, maybe you should not. You should probably just be listening. Do you see anything about the fraction that could be simplified before we did any radical stuff? The x's. Wouldn't one of the x's cancel out? It would. So I think maybe the first step would be to rewrite this as square root of 44 x to the what? Yep, x squared over 81. Notice how I've canceled an x out of both terms there, or both the top and the bottom. Or if you wanted to go back all the way to chapter 5, couldn't you say I subtracted my exponents? X to the 3 minus 1, it's the same thing. Okay, so from here, let's see if you guys can take it home. Okay, ready, set, go. Guys, I saw a lot of good answers. I'm still seeing more good answers here. This should end up going to 2x times the square root of 11. Square root of 81 is 9. Guys, take a look. Hey, I think I got around to just about everybody, but in case I missed you, oops. Hey, you can't even see it. I'm sorry. There we go. That's the correct simplification. Do you have any questions? I'm going to show you one last thing here so you can be ready to go with your WebAssign. We're good? Okay. So here is this last thing here that I want to show you. And we're just going to do this down in this little practice at the board space. So if you have a fraction, say, let's do something real simple. Let's say you had some fraction that said simplify, and you had, the square root, you should write this down, of 4/7. Let's go with that. Square root of 4/7. Let's go through some of the steps maybe you would take. Couldn't you look at this and say the square root of 4/7 is really the square root of 4 over the square root of 7? It's following that quotient rule for square roots. And of those two radicals you see up there, do either of them simplify down? Yeah, the square root of 4 is 2. Yeah, so you could say that this is 2 over the square root of 7. And in a lot of circles, that is a perfectly acceptable expression. You're going to find that a lot of textbooks, a lot of teachers even, I don't know if I find myself in this camp, but a lot of folks are going to be uncomfortable with this answer, and here's why. They're going to be uncomfortable with the idea that we have what's called a radical in the denominator. Okay? And so you're going to find, I think you'll see this in your WebAssign, that there's going to be questions kind of like this where they say, all right, we've got this radical in the denominator, and we need to fix it. Okay? Again, there's all sorts of cutesy little analogies for this. I'll show you the kind of the process, and if you're struggling to remember it, I can share the analogy with you. If we want to remove the radical from the denominator, here's what we do. It's root 7, right? Here's how you get rid of the radical in the denominator. I'm going to multiply the bottom of the fraction by square root of 7. And whatever I multiply the bottom by, what do I have to do to the top? It's got to be the exact same thing. Yeah, so I got to multiply the top by root 7 as well. So if I do this, there we go. I end up with 2 times the square root of 7. And square root of 7 times square root of 7 is?
0.
Not 0. No?
It's what?
No? Wouldn't it be the square root of 49? And what's the square root of 49? 7. So you'd end up with this 2 root 7 over 7. Hosanna, I think I just heard you ask a really good question. 2 root 7 over 7 would be our final simplifying. So Hosanna, I think I just heard you ask, why would you have to do that though? Did I hear you right? So this is I think there's two reasons. I think one of which is a pretty good reason. The other one is maybe not as good of a reason. This used to be done before the advent of computers and calculators. This used to be done all the time. This was something that was considered standard practice. It made it easier to actually divide it out and figure out what the approximation would be. I think that's a pretty bad reason. A much better reason is, as you guys get into geometry next year, Algebra 2 later on, you're doing some stuff with trigonometry. Being able to recognize various forms of these radical fractions is a very useful skill, and I think that's why we still do it. Being able to recognize what's equivalent to what and be able to see this rationalization of something like this is actually a pretty useful skill. So, anyways, thought I'd throw that in there for you. You guys are all doing awesome. Be keeping up with your WebAssign. There is a video for tomorrow. Make sure you get the video in for tomorrow. And hope you have a great rest of your day. See you then.